Hello everyone, welcome back to my channel, and this is day 5 of solving GFG POTD series, and today's question is about burning tree. It's asked in many companies and it is one of the most important question based on binary tree. So the question says that given a binary tree and a node data called target, find the minimum time required to burn the complete binary tree if the target is set on fire. It is known that in 1 second all nodes connected to a given node get burned, that is its left child, right child and parent. Okay, so here in this given example the target node is 8. So at first second the 8 will get on fire, and then after each second the nodes connected to this particular target node gets on fire. So after 1 second 5 sets on fire, and then after 2 seconds 2 and 7. Then same goes on with 4 and 1, then 3, 6 and 9 and 10. So finally after 7 seconds the whole binary tree gets burned. So we need to return 7. Initially take the result value and we'll call the function burn time, sending root, target and result variables as a parameter. And then we'll check if the node is leaf, then we'll return -1. If the target is found, we'll calculate both left depth and right depth from that particular node, and then we'll take the result as maximum of both depths and we'll return 1. And if if that particular node is not a target, then we'll take two calls, which is left call and right call. We'll search the target in both subtrees, left subtree and right subtree. If the target is found, we'll take the DFS of that, and finally we'll take the max of both left distance and right depth with result, and finally we'll return the distance by adding value 1. The same goes with right subtree, and finally we'll store the value result, as we are passing result variable as a reference value. So it will automatically store in this variable result, and will finally return that particular result from main function. DFS function is to calculate the depth of the node from target. So the code goes like, if node is null, will return 0, and we'll pass two functions like left and right, and finally we'll calculate the depth by using 1 plus max of left depth and right depth. So in this way we can solve this question and find the number of seconds required to burn the complete binary tree. So let's compile and run. Let's submit. As you can see, it's successfully submitted, but the time complexity of this would be O of n square, as we are calling DFS call for each and every node while we are searching the target in left and right subtree. So the time complexity would be O of n square. So the optimal approach of this question would be to use map and queue. Let me explain the approach first. So this is a given binary tree, and we need to since we need to burn its left child, right child and parent from for a target node, we need to keep track of left and right and parent nodes for a particular node. So we can access left and right nodes using DFS calls, but how to track that particular parent node? So for this we need to use an extra space called a map, where while traversing that particular binary tree, we'll just keep the track of that particular parent of each node and we'll map it to that particular node. So while traversing that each node, we'll push all those left and right nodes of that particular current node, and parallelly we will keep map those nodes to its parent. So we'll do a level order traversal of this binary tree. Then we'll push its left and right node in the queue, and meanwhile we'll update the parent node of each left and right node. So after all the traversal of the binary tree, the map looks like this, where initially the parent of root node would be null, and the parent of 2 and 3 would be 1, and 4 and 5 would be 2, and 7 and 8 parents would be 5, and same goes with 6, 9 and 10. So after finding the parent nodes of each and every node, and as we know the left and right nodes, it's time to burn each these three nodes of each and every particular node. So we need to burn left child, right child, and its parent node. So we'll take the help of queue, and we'll start burning the node from the target node. So initially we'll push the target node into the queue 8, and then till the size of the particular queue we'll run that loop, and we'll pop the front node from the queue, which is 8 initially, and we'll burn the left and right child and parent of that particular node. So since 8 doesn't have left and right, but it has parent 5, so we'll mark it as visited, like we'll mark it as it's burned. So after marking it as visited, we'll push it into a queue and we'll increment the time of burning. So initially it would be 1. The same goes with 5. The child of the left and right child are 7 and 8. So since 8 is already visited and it's already burned, so we'll ignore that, and we'll burn 7 and push mark it as visited, and we'll push it into the queue. So the parent of 5 would be also 2, so we'll also mark it as visited, and we'll get it burned and push it into the queue, and we'll increment the time by 1. So the time till now would take 2. So the whole process from here goes on, like the 7, when it comes to 7, the front of the queue would be 7. 7 doesn't have left and right child, and its parent is also visited and burned, so we'll ignore 7. And when it comes to 2, 2 has left child 4, right child is already burnt, and it has parent 1, so we'll push 4 and 1 in the queue. And when it comes to 4, it doesn't have left and right child, and its parent is also visited already, so we'll ignore 4. And when it comes to 1, the left child is already burnt, and it doesn't have any parent, and we'll push the right child 3 into the queue. And meanwhile we'll increment the time of the burn from 2 to 3 and 3 to 4. It goes so on and so forth till 10, and finally until or unless the queue becomes empty, we'll increment the time of the burn, and finally we'll get the result as 7, and we return this 7 as answer. So the code of this approach would be like this. So we'll create a map which keeps tracks of node to the parent, and then we'll find the target node, which is 8 in our case, using create mapping function. Create mapping function generally does the level order traverser while keeping track of the node to the parent mapping. It initially pushes the root into the queue and makes map of that particular root as null. Since root of the tree doesn't have any parent, we'll map it as null, and then we'll run a loop until or unless this queue becomes empty. We'll pop the front node, and if we'll check if that particular node is a target node or not. We'll store that value in a result variable, and meanwhile we'll push all its left nodes and right nodes into the queue while keeping track of those node to its parent. So we'll map all those value to its parent, and this function generally creates mapping from that for a node to its parent. So after creating the map, we'll calculate the time for burning a tree from that particular node to the and by using the map of node to parent, and finally we'll return that time to get that minimum time to burn the whole binary tree. So this function goes like this. We'll use a visited map whether that particular node is already burnt or not. So we'll start by pushing the target node into the queue. We'll initially we'll mark it as true as it's burnt initially, and we'll take the variable minimum time. So until or unless this queue becomes empty, we'll run a loop and we'll find the length of the queue, and we'll find the front node, we'll burn its left child, we'll burn its right child, and we'll burn its parent child. And keeping track of each and every child will make it as true as visited, which means it's already burnt, and parallelly we'll push all those value into the queue. So after all these operations, we'll increment the time by 1. So until or unless the queue becomes empty, the time increments by 1, and finally we'll return that particular time from this function. So finally we'll return time from this function. So let's compile and run. So let's submit. So as you can see, this problem is also submitted successfully, but the time complexity of this will be O of n at worst, and the space complexity would be also O of n, as we are using extra space, extra map, and queue. So in this video we have observed two different solution, but with different time complexity and space complexity. I hope you like this video and explanation. See you in the next one.